Okay, so we are back again. So actually I didn't make notes for this, just see how this. First you write down all the state variable equation, right. So first if you write, this is plus sign, right, this is plus sign. So say x1 is equal to your kp upon 1 plus stp, right, in bracket, this is x2 minus delta PL, right. So from here you find out equation of x1 dot, right. So you please write down, here difficult to accommodate all these things. So you please write down what is x1 dot, cross multiply and simplify. X already we have seen there. Similarly for x2, I am making it here, x2 is equal to x3 divided by 1 plus STT. From here you find out x2 dot, right. And similarly for x3 I am writing here, right. So x3 will be is equal to your, this is x1 here coming here, and this is x4, and this is actually plus, right. So x3 is equal to x4, because this one we have taken as a state variable. So it is x3 is equal to x4 minus your x1 by r, right, divided by 1 plus STG, cross multiply and find out your what is x3 dot is equal to, here also what is x2 dot is equal to, right. So this way you have to take. Similarly for x4 is equal to, it is minus ki upon s, and this is delta f means it is x1, so into x1, right. So if you cross multiply, x4 dot will be minus ki into x1, right. So x1 dot, x2 dot, x3 dot, x4 dot, if you take, you just your, then what will be your order of A matrix? It will be 4 into 4. So you can write x dot is equal to x plus bu plus gamma p. So x, that means your A matrix is a function of ki, right, and other parameters are known to you except ki, and you have to find out ki using degree of stability. So I suggest, so I am now clearing this one. So I will suggest that you will write x1 dot is equal to equation x2 dot, x3 dot and x4 dot. So your A matrix will be 4 into 4. Here our interest is only A matrix, because A matrix is function of ki, right. So because we have taken that control variable u as a state variable, so that is your x4, right. So that means A matrix is a function of ki. So it is a 4 into 4 matrix. Now what you will do for degree of stability, that you find out the eigenvalues of the A matrix, right. You will lambda I, A minus determinant of A minus lambda equal to 0, you find out the your eigenvalues, right. Generally that lambda is like this, but this has become my habit, right. So A minus lambda I equal to 0, determine that and find out eigenvalues. So there are 4 eigenvalues, because your A matrix is your 4 into 4, so 4 eigenvalues. It may be eigenvalues, maybe 4 are real, or maybe complex conjugate pairs, or 2 real, 1 complex conjugate pairs, it may be like this. So that is not the case, you will get 4 eigenvalues, right. So lambda 1, lambda 2, lambda 3, lambda 4, if it is complex conjugate also it does not matter, but 4 eigenvalues. After that the concept is the degree of stability, right. So you know these eigenvalues, right, you know that you see that this is my real part and this is my imaginary part, right. So if your system is stable, all the eigenvalues will lie on the left half of the S plane, right. That means their real part is say negative. So if suppose for example, just for the sake of your clarification, suppose we have one complex conjugate pair eigenvalue, so it will be located here, it will be located here, say other two are real for example. So one is located here, another may be located here, right, or maybe somewhere, or maybe your another also may be complex conjugate, right. It does not matter pair, it does not matter. Our objective will be for degree of stability, that is we define as a rho, right. First what you do, that rho should be that eigenvalues which will be very close to the origin, this is origin, is most sensitive for your instability, right? Because if it moves to the right half of the S plane, then your what we call system will become unstable. So, eigenvalues which is very close to the origin, that is our your what you call interest, because that eigenvalue is more sensitive to the stable operation of the system. Other eigenvalues away from that, that is our not consideration. So, our consideration is which is very close to the origin, right, and that means we have to see the real part. That because even if it is complex conjugate also, suppose if it is complex conjugate also, so you have to see the real part, right. So, our objective is that push this one to that away from the origin. Therefore, we can define rho is equal to, right, rho is equal to, we have to find out your this thing max of, that is maximum of that real part of lambda I, right, for I is equal to 1, 2, say here 4, right. That means, we will take the real part of the lambda I, then we will take that your max value, because all eigenvalues are negative. Suppose one eigenvalue is minus 0.1, another is minus 0.3, right, say 0.1, then minus 0.3, another say minus 1 plus minus your j2, right. So, something like this. So, out of, if you take the real part of all these 4 eigenvalues, so it is minus 0.1, then minus 0.3, then minus 1.0, then minus 1.0, because complex conjugate pair. So, minus 1 minus, out of this all these 4 it is all minus. So, maximum you have to take. So, this is the maximum, right. That is why you write rho is equal to maximum of real of the lambda I, right. So, that means we will take the max of real lambda I, because it is your what you call that is eigenvalues which is very close to the your what you call at the origin, and our objective will be push that eigenvalue to away from the origin such that system will become stable. So, in that case what we will do, that in that case you plot what you will do, suppose this is my k I values, because A is a 4 into 4 matrix and this is my rho, that is degree of stability, right. So, and this is origin. So, in this case what you do, you start from k I is equal to 0, then next value of k I is equal to 0.5, say 0.10, then 0.15 like this. In a step of 0.05 you change the value of k I, and every time you find out the eigenvalues. Using say MATLAB, you put it in a MATLAB, every time you put in a loop and find out the eigenvalues of A matrix, that k I is equal to 0, k I is equal to 0.5, and every time you find out what is the value of rho. That means, this will be your k I and this will be your rho, and rho will be, I told you, it will be real of, it is sorry, maximum of that real part of lambda I, right, this is rho. So, this is k I, this is rho, say 0 find out rho, then 0.05 then find out rho, 0.10 find out rho, right. So, all these value you find out for the rho, this is k I, this is rho. After that you plot it. So, if you take k I, as soon as you will plot it, what will happen, you will observe that graph will be something like this, it will come and finally it will go to like this, right. That I mean it will go like this. So, in that case what will happen, that this value, this is the maximum value of the rho, this is your rho max, that is this is the maximum, that means this is the maximum that you can push that eigenvalue which was very close to the origin away, much away from that. You cannot go after that, even if k I is increased, it is actually decreasing, it is actually decreasing. So, this value we call k I optimum value, and this is that, this is your what you call most critical value of k I. Beyond that it will become unstable, because eigenvalue will move to the right half of the S plane, right. So, this rho versus k I plot, from there you will get your optimum value of k I, but this is not like that, that it will give you the best response, right, but it is one way to your find out the optimum value of k I, your this thing, or what you call using degree of stability. Similarly, if you use proportional controller or your PID controller, there also you can easily find out that your what you call that your this thing, that Ki, Kp, Ki proportional gain, derivative gain, integral gain, but your what you call, you have to call 3 together, you cannot do it. First you optimize Ki, fix the value of Ki, then try to find out the Kd, right, then you try to find out the Kp. This way you have to try. But if we put PID controller also this way, only thing is that X4, if you put PI or PID controller, only modification you have to make for your X4 dot equation. For example, suppose this is my controller, right, and this is my PID controller, right. Say proportional gain is say Kp dash, because power system gain we have taken Kp, say it is Kp dash. Rather I can put it like this, say this is my PID controller, say I can take this is K1, right, and then say this is my SKD, that your differentiator, that is your differential part, and this is my Ki upon S, right. Take one thing is there, that if you take your this, you take minus K1, just hold on, I will change the sign, right, and I will give you this question. Suppose this is minus K1 minus your Kd SKD and minus your Ki upon S, and this is your X4, that is nothing but your u, the control variable, and this is input, the frequency is equal to delta f, right. So, it is Kp dash you take, because your power system gain has been taken as your Kp, right. So, it is minus SKD. So, I will put a question, if when you take minus, we will take Ki, generally Ki, Kd, and it depends of course on the system. For this system Ki, Kd or Kp you have to take positive, but if you take plus Kp dash plus SKD plus Ki, then you have to take Ki negative. So, we have to see that. By chance if you see that eigenvalues are your what we call system going to right of a base plane, then be careful about the sign, and this is a question to you, that why it happens, right. If you put minus Ki upon S, then Ki is positive. So, why it happens? This is a question to you, technical question to you, right. So, and this, if this is X4, if you take like this, then and this is X1, then what will happen, that X4 will be is equal to, just I am showing that how we will write down the equation. This is Kp dash, and this is your minus SKD, and this is your minus Ki upon S into your X1, that is X4. Now, both side you multiply your what you call your X4 is equal to X1 this one, right. So, what you can do is that both side, if you this thing, if you try to find out that your SKD then Ki upon S. So, how to actually your evaluate this one. So, in that case process will be little bit complicated if you consider all these three. Suppose if you take that your X4 dot, so you have to multiply both side by S, right. So, in that case this will be also S, this will be S square, that means double derivative, and this will be your, this S should not be there because it is multiplication. So, in that case it will become minus S Kp dash X1 dot, and it will be minus Kd into X1 double dot because of S square. So, you have to find out X1 dot is known to you, then you have to take another derivative, and you have to mathematically you have to manipulate everything, and then you have to find out, right. So, the procedure in that case little bit your complicated, but it is possible to make it because this S X4 is X4 dot, but only thing is that so many elements will come, right. So, that is your what we saw, that degree of stability, and this is we have seen. Now, next one is that concept of control area. Now, consider a practical system with number of generating station and load. Suppose you have number of generating station and load. So, AGC problem of a large interconnected power system has been studied actually by dividing the whole system into a number of control areas. We call it is a control areas, right. So, a control area is defined as a power system or a part of a system or a combination of system to which a common generation control scheme is applied. So, basically when you say that control area, actually it is a power system or a part of a system or a combination of system to which a common generation control scheme is applied. Suppose in a particular power plant you have n number of generators. So, all these generators actually in that we will assume they are in coherent group. That means coherent means that means they swing in unison, that means any load changes this increase or decrease of the speed will remain same, right. So, that is so in this case, just hold on. So, the electrical interconnection within each control area are very strong, right. So, the electrical interconnection within each control area are very strong as compared to the ties with the neighboring areas. That means, suppose you have a power system where you have many generators, many bus substations, right. So many lines are there, and you have another power station, a power system, suppose 400 kilometers away from that. There are also so many lines are there, interconnected lines are there, right. And these two power systems are interconnected by tie lines. We call it, basically it is a 3-phase transmission line. Whenever it is because of the power exchange, either from this control area to that, from that control area to this, based on several criteria, right. So, that is why compared to ties with other neighboring areas. So, all the generators in a control area swing in unison or coherently, and it is characterized by a single frequency, I told you, right. So, in normal steady state operation, each control area of a power system should strive to meet its load demand. Suppose two power systems are interconnected, later we will see. So, and suppose power system A is somewhere here and power system B is 400 kilometers away from here. Suppose there is a load disturbance in power system A, load increase say. So, that generating units for that power system will accommodate that load. By chance, if generation is not sufficient to accommodate, that means it has to borrow or buy power from the other interconnecting areas, right. So, simultaneously that each control area of a power system should participate in what you call in regulating the frequency of the system. So, the two basic inter-area regulating responsibilities of each control area are: first one is that when system frequency is on schedule, each area is expected automatically to adjust its generation to maintain its net transfer with other areas on schedule, thereby absorbing its own load variations, right. So, so long as all areas do so, schedule system frequency as well as net interchange schedules for all areas are maintained. That means that you have, suppose you have two areas, it is interconnected by tie lines. Tie lines, I told you, it is 3-phase transmission line. Suppose when it is connected to two tie line, some schedule power will flow, because they have some what you call some agreement, right. Suppose at 10 o'clock area A needs 100 megawatt power from area B, that is your other power system. So, as long as it is on schedule, right. So, what will happen, that whatever it is written here, that when system frequency is on schedule, each area is expected automatically to adjust its generation to maintain its needs transfer with other areas on schedule, thereby absorbing its own load variation. Suppose area A, that load change, so it is expected that area A power system generating units will absorb its own load variation, such that frequency also will be maintained at its schedule value as well as that interchange power also. But of course, there will be little transient imbalance, but ultimately it will achieve its objective. Now, second one is just when the system frequency is off schedule, when it is not, because one or more areas are not fulfilling this regulating responsibility, right. Other areas are expected automatically to shift their respective net transfer schedule proportionally to the system frequency deviation, right, and in direction to assist the deficient areas and help to restore system frequency. The extent of each area's shift of net interchange schedule is programmed by its frequency bias setting, that we will see later, right. Failure of an area to respond fully to frequency deviation caused by other areas create extra regulating requirements for areas that do not properly respond. So, before going to actually deregulated system, all these things we have to study. Then we will find deregulated system, because simulation thing is not our purpose for this course, because we have to see from the point of view of the classroom exercise, right. So, now if somebody asks you what is the advantage, that is of the what you call interconnected operation. So, this is that your maybe the answer. The cooperative assistance between areas is one of the planned benefits of interconnected operation, right. But that means this is the thing, the cooperative assistance between areas in one of the planned benefits of interconnected operation. But when the assistance is unscheduled, it is obtained at the expense of departures of system frequency and area net interchange from their respective schedule, right. Actually, this integrate respectively into system time deviation. This will not study here, right, the time error. This will not study here, and area unscheduled and inadvertent interchange, that is your inadvertent interchange means it is energy, right, that will not study here. Then things will be much more, that length of the lecture will increase, right. So, we will not do that, right, and cause additional regulation on the part of your assisting areas, right. So, now with that is the thing, we will come to that your area, your what we call 2 area and other equations, everything, or derivation mathematical model, but before that we will see 1 or 2, 3, 4 examples, right. So, first one is this second example 2, a power system has a total load of 1260 megawatt at 50 hertz. The load varies, this we have seen also before, that 1.5% for every 1% change in frequency. We have seen that how to find out that your R values. Find the steady state frequency deviation when a 60 megawatt load is suddenly tripped, right. That means, if there is no speed control, that means that speed control mechanism is not there, and B, the system has 240 megawatt of spinning reserve, right, evenly spread among 500 megawatt generation capacity with 5% regulation based on this capacity, right. Assume that the effect of governor deadband is such that only 80% of the governor respond to the reduction in system load. Actually, governor deadband will if time permits, I will tell you at the end, if time permits, that what is actually definition of every system you can find deadband is there. So, definition of deadband nothing will discuss here, but from the sake of this numerical we will only study that one, right. So, if time permits, it actually deadband actually it makes continuous oscillation in the system frequency and type power deviation, right. It sometimes is called backlash. So, this can be studied, many mechanical system, anything you will find that your deadband is there, different type of deadbands are there, right. So, even in your cycle chain and the thing also you find the deadband is there, but from here those things I should not explain that, right. So, deadband will be, backlash will be there, right. So, assume that the effect of governor deadband is such that only 80% of the governor respond to the reduction in system load. If time permits, half an hour I will explain governor deadband and mathematical formulation also. It will not take time if time permits, right. So, solution is total, that is it is given that your that when a 60 megawatt load is tripped, that means load actually is fallen, decrease, that means what, in general the frequency will increase, right. So, first thing is the total remaining load now will be 1200 megawatt, because 60 megawatt load tripped, right. The damping constant of remaining load is, it has given now 1.5% of change of total load is equal to 1% change in frequency. So, I have just make it this one divided by this one, that is why it has actually, if you write like this, also it is okay. If I write like this, that 1.5% of 1200 divided by that 1% of your 50 hertz, right. So, this is 100 has taken like this, right. So, this is actually you get it 36 megawatt per hertz, right. So, this is that value of the D. Now, part A given with no speed control, resulting increase in steady state frequencies delta FSS minus delta PL upon D. Actually, we have seen the steady state value, right, delta FSS is equal to your minus delta PL divided by D plus 1 upon R, right. As no speed your what you call no speed governing system is there, right, speed control nothing is there. So, this should not be there, that is why this equation only minus delta PL upon D, right. That means, and it is minus, then load has tripped. So, if actually convention is, if load has increased, if delta PL, suppose had it been load has your what you call decreased, so you have to take minus 60 megawatt, right, and if load has increased, then you will take delta PL is equal to 60 megawatt, right. So, for increase of the load you will take delta PL value positive, and for decrease is load you will take negative. So, it is minus of minus your 60. So, that is actually 5 by 3, that is 1.677 hertz. So, simple thing. Now, the total spinning generation capacity is equal to load plus reserve, right. So, this is actually load 1260 was there, and spinning generation capacity is, that is a spinning reserve, that means total is 1500 megawatt, right. Therefore, generation contributing to regulation is, it is 80% of that, right. So, 0.8 into 1500, so basically it is 1200 megawatt, right. So, a regulation of 5% means that a 5% change in frequency causes 100% change in power generation, right. Therefore, we can find out R. So, 1 upon R I have written, so it is 1200 divided by 5% change in frequency. So, it is megawatt, and 5% change in frequency, that is 5% change in frequency causes 100% change in generation. So, total was 1200, right. So, 100% means 1200. So, that is why we have written 1200, right, and 5% change in frequency, right. So, that is your 1200 by 0.05 into 50, we have, it is a 50 hertz system. So, it will be for 480 megawatt per hertz, right. So, that is your 1 upon R. Therefore, the composite frequency response is, sometimes we define that is beta, we call it is frequency response characteristic, or sometime, right. So, beta is equal to D plus 1 upon R. So, D we have already got your what you call 36, and this 1 upon R is 480, right. So, total is 516 megawatt per hertz, right. Therefore, the steady state frequency is, so load is decreased, right. So, basically it is your delta F S S minus delta PL upon beta, beta basically it is your, this term is actually minus delta PL divided by D plus 1 upon R, that is our beta, that is our beta, right. So, it is load has tripped, so it is minus of minus 60. So, 60 upon 516 hertz, so 0.116 hertz. So, this is the your answer, right. So, problem is very simple, and your this is so far whatever we have studied, that isolated system, and your little bit on degree of stability also I told, it can be applicable to any other control system also, right, but it is a video course. So, all these things cannot be put it to here, right. I have to think from the point of view of classroom exercise. Thank you very much, we will be back again.